Next part is also somehow related to the system level and how you make your model better, let's say. So I want to speak about how to extract important effects from 3D analysis. It's typically parasitic effects, what you maybe in the initial design would not take into account, but to have more predictive power, you want to, let's say, enrich your 2D finite element analysis with its effects. Okay, motivation is, you definitely don't want to simulate your machine or at least characterize your machine in 3D. So it is a 3D device, but due to its nonlinearity, this quite complicated winding, the rotations, the saturation effects, which means for every operating point, you have to run many transient, many time steps, and for each one a different finite element analysis, a transient one. It's prohibitively large to being practical. And therefore, we have to come up with ideas how we can incorporate the most important effect in the most effective and most accurate manner. And here I give some ideas how this can be done. So in the following, I will call this method 2.5D. I don't know whether it's a common terminology, but so please remember when I speak about 2.5D, it means 2D plus this stuff we extract here. Okay, we take an example. It is actually the same example what also E was using for his optimization. It's created out of our library. It's right, as our library. It's 48 slot for pole pairs, some common design for a traction drive. It's 150 millimeter long. And you see here it has around, you cannot directly, so around 380 Newton meters. Again, we assume 18 amperes per square millimeter RMS current to be the maximum current loading, which leads to roughly 260 ampere peak current. And since we want to extract at one particular operating point, we choose the operating point where you are most likely in. So sure, we don't have the knowledge where you are exactly most of the times. You can use here some driving cycles or something like this to find out. For us, we do it easy. We just say, okay, we take 60% of max current as an operating point, which is most likely something realistic over a right operating regime. Okay, this means 450 ampere, beta of roughly 43 degree. This is what we are dealing with in the rest of the presentation. And the results we see here come from machine task, a DQ model generation, which creates this nonlinear map. You get the information, what load angle you have to set, and from this one you can beat off what I just said. And here, pure 2D, distributed coils, no losses, no skewing, nothing fancy. Okay, so now what effects do we want to include? First of all, losses is an important aspect. The losses in the coil you can incorporate quite straightforward. So you use solid CAD coils, and you have here the individual conductors, and then you get the eddy current losses in this one. However, with magnets, it becomes a bit more complicated because you don't know exactly what conductivity you should use in the 2D analysis. This is seen better here because often in reality you skew the machine. It's one aspect. So you make a shift between individual sections of your rotor, mainly due to reduce higher harmonics. But another effect is that you have segmented magnets. So instead of having one long magnet, you have in this case 4 individual sections. And this will reduce the eddy current losses. And we somehow have to incorporate this effect into an effective conductivity. And last but not least, quite obvious, you have here this overhang. And this overhang obviously have resistance and have also additional leakage inductance we somehow have to incorporate. Okay, looking first at the skewing and the segmented magnets. So why we do it? I already briefly discussed this. So in the first place, we want to reduce harmonics, mainly the air gap flux harmonics, which are shown in MMF. MMF, magnetomotive force. So this is the flux in the air gap. And when you decompose it, you can do it analytically. We have here a winding tool from Opera, which shows you how the harmonics are distributed. Here we have the frequency axis, here we have the relative amplitude. And you can play here first with your winding scheme, which is given because we have already chosen on our machine, but you can also play with the skewing angle. So actually the angle between the top row and the lowest row of your magnets. And here you see directly, even in an analytic way, that the harmonics goes down considerably when you choose here a skew angle of 7.5 degrees. And with load scenarios in the machine task, you can also directly compare the torque and the voltage, and you see, yeah, it really works as expected. So the harmonics, or the rippling, reduce dramatically. Okay, how you can do this? Each of the drive scenarios in the machine task have a setting regarding skewing, and you can switch on here finite skewing, gives the maximum skew angle, and either define it by the number of steps or by a uniform skewing, defining here relative length and the angle of each section. And then you get results, including skewing. So what happens under the hood is you do for each section a separate finite element analysis, leading to 4 different torques, per example. It's shown here in the plot. So we have here parameter sweep, completely done without user interaction. So this is what the machine does set up. You have here your 4 different torques, and the average sum of this, so average means averaged by the relative length, gives you the torque of the skewed machine, which you find then directly under machine task results. So this post-processing is done automatically by the machine task. Okay, this was the first effect. The second one, as I said, is the segmentation of the magnets. And this is definitely a 3D effect, so we cannot incorporate so easily. So the idea here is we take half of a section, so have an boundary condition here, which keeps the field normal, so the current normal. These are the eddy current lines here, and have an isolating boundary here on the top side. So, and then we run a particular load. In this case, it is the load point we have chosen. This is 45 degrees load angle and 450 amps, and beside of this nice picture of the eddy currents, we also get losses. And when we scale the losses then from a half of a segment, what we simulate here, up to 4 segments, we have losses over time from the 3D simulation inside of the magnet, which average to 2.65 watt at 1500 RPM in this case. So now the goal is to determine the effective 2D conductivity, which gives the same amount of losses. And here you can make a sweep or use an optimizer, but since it's more or less linear in this case, sweep is maybe easier. You run some points, in this case 0.5, 0.6, and so on, and you find the point where you reach this 2.6 watt average loss. And on the x-axis, you see here then the parameter, so the 2D permanent magnet conductivity, and you find out 1 millisiemens per meter what the magnet is assumed to have in reality have to be reduced to get the right amount of losses in 2D. So you have to reduce here up to 0.69 megasiemens per meter. So now the effect of skewing is incorporated. So next we are looking at the winding overhang. So I have to introduce a bit of theory so that you can understand what we are trying to do here. There is, let's say, one fundamental equation. So the terminal voltage, so the voltage you see at the terminals of your machine, is decomposed into resistive part. So the resistivity of your windings multiplied by the individual phase currents, and then an incremental inductance matrix times the time derivative of your currents and a motion-induced part. And in the subsequent slides, I will call this part here, which is related to the induction matrix, inductive induced voltage, so UL. Please remember, because you will see it on many plots afterwards. So the interesting thing is this one can be, both the incremental inductance matrix and the motion-induced voltage are results you define a monitor for. So they are built-in monitors in CST, in 2D and in 3D. You just define an incremental inductance matrix, and then you get these two quantities. So the complete matrix and the motion-induced voltage. Important is, due to saturation and also so rippling and the dynamic nonlinear behavior of the machine, will make these incremental inductance matrix time dependent. So you have here an oscillation both in the diagonals and in the off diagonals, but they are repeating. So obviously A phase, B phase, C phase behaves the same, but with some phase shift in between. So this is why we can look now at one off diagonal and one diagonal in the following. Okay, and what we want to achieve, we want to find out the overhang resistance in such a way that the resistance used in 2D plus the overhang resistance give us the real 3D resistance. And the 3D incremental inductance matrix should be decomposable into the 2D incremental inductance matrix plus a matrix with constant terms, and actually just two constant terms called L and M in this case. And maybe an additional one things first, a simplification, but actually it isn't. So we can also take this matrix and make a diagonal matrix out of it. And these diagonal terms I call here LOH for overhang. So please remember, these overhang inductances is what we want to determine. So, and the analytical connection between these two is the overhang inductance is L minus M for a symmetric V-phase system, what we have here in this case. Okay, when you think in terms of circuit description, it would mean we have what happens in 2D. So we have here the finite element coils and 2D resistance. And we have then lumped parameters describing the winding overhang. And here we have the terminal nodes. So actually the star point here and the outside terminals where we apply the source here on the upper side. So these two things we want to determine. So this is the goal here. How we can do this? First, we can look at the DC resistance of the overhang. You can take a volume and cross-section and calculate something analytically, but maybe easier, at least if you have already the CAD model, is using the stationary current solver. So you take your cut, transfer it into a coil. It's a functionality in CST. Every CAD, you can make a coil out of it if it's closed structure. And closed in this case, it's, yeah, in reality, it's closed, but we are simulating just a piece of cake as we did in 2D. So, and since it's a parametric model, we can also set our stack length, so LFE, the length of our iron stack up, to 0 millimeter. And by doing this, we have a quite simple model. We're just looking at one phase. We excite a current. After mesh adaptation, we just have 92 tetrahedrons. It takes a few minutes. Meshing is the longest part of it. Then we can calculate the overhang resistance. It's just the losses divided by the square root of the current. So, okay. So overhang resistance at DC is determined. So we remember it's roughly 3.4 milliohm. So more challenging is the inductance. So, and the idea here is the following. Since we can simulate 3D and 2D, we choose a particular stack length and compare the 3D incremental inductance matrix with the 2D incremental inductance matrix. both for a diagonal term and for off-diagonal term. So what you see here is not the inductance matrix, but the difference between 3D and 2D, and for different lengths. So, in the top row, you see a comparison between 10 and 20 millimeter stack length, then 20 and 30, and then 30 and 40. And when we look here to these plots, you see that the difference becomes lower as longer the machine gets. And from this, we conclude that in 40 millimeter, the complete behavior of the overhang is incorporated in the induction matrix. So there is no reason to simulate a machine longer than 40 millimeters to extract this. And 40 millimeter is already something, but the good thing is we can simulate it still in one night. So we can use here time symmetry. So it's 1/3 periodic. So meaning we simulate 30 time steps in this case. We end up with 1.9 million TETs with a 40 millimeter stack up. So the mesh you see here on the top right. And in a quite old workstation, runtime completely including meshing was 13 hours. So if you go to so leave your office in the evening and come back at the next morning, you have all the data you need. Okay, so we are using this difference now to determine L and M. And this we can do based on RMS and peak combinations. So here is an example of the formula used for it. So we take the difference, multiply it by the time derivative of the current, takes the RMS value of it, multiply it by square root of 2, which is something like the average peak value. And this should be L times the peak value of I dot. And the peak value of I dot. And IA is given, is known, it's and is sinusoidal, so you know everything, and then you can find out this inductance L. This is similar, you can also do it for M. And when we look carefully at what we achieved so far, we take this 3 different voltage contribution from each of these row of incremental inductance matrix separately, and compare one period for each of this term with pure 2D, the 2.5D, so the one with these parameters we have extracted, and the 3D results. Looking carefully, or maybe directly, you see that the black dashed line is is a bit off. So we go already in the right direction. And how well this works, we see better when we are looking at the full inductive voltage. So not in the individual parts, but it's the sum of all of them. Because the only thing you see when looking from the terminal is the full voltage. So you have no access to the sum. And when you sum it all up, you get one period of the voltage. And here the effect is much stronger. So you see that this dashed line is much, the distance is much higher. And a good measuring of the difference is the RMS values. And when we calculate RMS values for each of these curves, you see that with the 2.5D comes up to 1.4% to the 3D result, whereas the 2D just has 15% difference to the 3D result, which is quite a lot. And okay, so up to now I speak about L and M. So obviously I introduced already the analytical formula. LUH can be calculated as L minus M. So 9.27 microhenry is the value what we extracted for our machine. Okay, but okay, so maybe this value doesn't give you a feeling how important is it to incorporate this effect. But the machine task has a possibility for each of the drive scenario to define the overhang resistance and overhang inductance. What it does then under the hood is after the simulation is done, each inductance, each flux linkage, each voltage is corrected, because when you're knowing this value, you know the additional voltage drop in each of the phases. And taking this into account when calculating operating points, you see a quite considerable difference in the operating regime you deduce from the loss map drive scenario. So here on the top right, we see the difference in power versus speed. So you see here with no overhang, you would say, okay, the markers are here. You have 233 kilowatt max power. Whereas when you use the overhang parameters, we just determined you have 10 kilowatt less. And also at high speed, you also see a reduction. So, okay, and this I would say shows quite considerable influence. So therefore, I would say for good predictive power of your simulation, you should always include the overhang resistance and inductance. Okay, there is another possibility often used in, let's say, competitor tools, maybe, and also what maybe you are used to in Opera when you set up such things. You couple finite element with the circuit description. This is also possible in CST. So, but to be honest, we don't have a GUI, so this is not coming from a GUI which set up these circuits. But we have for machines default circuits scriptable, not scriptable, parametric. So you just choose for the circuit you want, either an active short circuit, which is the more complicated one, or current-driven delta, voltage-driven delta, and then you get such kind of circuits. You get circuit results, and you can compare then directly with the post-process results from machine task. And this is what I have done here. And you see really good match. So actually, this is expected. It just shows that everything is consistent. But just to give you a feeling that we have these two possibilities. And especially this one gives you freedom also to do something like short circuit analysis and these kind of things. So you can play with switches. So it gives you the circuit description. However, taking it into account over the whole operating regime is not so not so handy than the post-processed approach from machine task. Okay, last thing what we didn't speak about yet is again coming to the losses, because obviously when you go with higher speeds, you have more and more eddy current losses in your winding overhang. And up to now, the resistance was just a DC resistance. Remember, it was the stationary current analysis, which gives us a 3.5 milliohm. So, however, we need the right losses in the winding overhang, in particular when you go to thermal analysis. You remember in my first talks this oil spray cooling of the overhang, and what you need here is the right volume losses for this winding overhang to get good predictive power and such kind of analysis. So, and what we do here is we use frequency domain. So saturation and magnets is not so important when looking at resistance. So it's the dominant effect is here the nearby flowing currents of the nearby conductors, and this can be completely analyzed in frequency domain. So we take again our 40 millimeter, which we know is long enough as a baseline. We go a little bit lower, so we do two simulations, 35 and 40 millimeter. Assume some linear permeability, 500 in this case, for rotor and stator. Simulate up to 15,000 RPM, which means in frequency range, we're going up to 1000 Hertz. Choose 120-degree phase shifted current at 450 amp peak, because this was the operating point we were looking for. And nice thing is the overhang power, the losses in the overhang should be a constant. It should not change when we go from 35 to 40. And this enables us to get from these two analyses a value for the overhang losses over frequency. And from this one, you just divide by the square root of the current, and you get your AC resistance as a function of frequency. And you see here, it fits quite well with the overhang resistance from the stationary current solver, because we can take here the limit to the frequency 0, and we find that we have here 3.449, so which is 3.45. And this is, in the numerical accuracy, the same as the J-static solver. And what we can do with it, we can go in Daimler and now take care of these losses on the system level. And since we already make it as a 1D lookup, it is quite easy. We can use the built-in block. It's an SDF ND table. We only use here a one-dimensional lookup. The interpolation is done in this one. We just load the data. The input is the derivative of the angle sensor. So actually the derivative of the angle, which is omega. Here is then the lookup resistance as a function of omega. And these are variable resistors, which then take care that we get the proper losses here. Yeah, and this close the loop. So I guess I have done all what I promised in the beginning. So we look into the different aspects of 3D effects, which have to be taken into account. Segmented magnets, the overhang, the skewing, and the AC losses. We saw that 2D analysis is considerable off when it comes to the operating points you determine, especially in the MTPV region. That's meaning at high speed. You can do it, let's say, quite cheap because you simulate a short machine, you simulate just one and lossless in 3D, and this gives you enough information to extract all the values you need. Okay, and incorporating this is also shown, and it's quite easy in a machine task, circuits, and the AC resistance and the system level. Okay, with this I'm through and open for questions.